I. Then the value of this function is already done inside of here. Because this is, yeah, times. And not only that, this function has a point. It becomes infinite when where alpha 2 omega plus 2 omega to the I. So there's somewhere some this point. There, this function becomes denominator becomes 0, so it's kind of the infinite becomes. In the today terminology, this function has a pole at that point.
That point should be alpha plus something. It's not
Data I. Where? Oh. And also, not only that, there's another one. Here, this is 2 omega plus 2 omega to the I plus omega plus omega to the I. There are also two points inside there. Here, that phi becomes infinite. In the modern polynomial, it has a pole. Okay. So in this way, Abel succeeded to define the sum function, which is a periodic function with two independent periods, and usually it's called the elliptic function. And then it's called that elliptic function. So Abel found that some example of elliptic functions. Yeah, in a sense, it's sounds very special because this fundamental domain is the rectangular. Okay. So this is a starting point, and Abel, is interested in this addition cell. So he really wanted to know that what is phi 2 alpha, phi 3 alpha, and phi 4 alpha, and so on. He really wanted to using this formula to calculate. So it's a 2 alpha is very simple, but 3 alpha is a little bit complicated, but it's inductively you can define. And he found, rather surprisingly, that relationship with the equation solution. And what he found is, if n is odd, then not necessary. N is odd, yeah, that's better. In alpha, we can write down something at Pn of I alpha. No. Yeah, Pn of I.
just n's polynomial.
And both are polynomial. Of actually degree n squared.
N square.
N squared. And what this mean? So starting from the phi alpha. So of course that this is just starting from the phi alpha. You can write down everything that expressed in nice way. But Abel considers in the opposite way. If you know this number, what is this root? Okay. So you can go in the opposite way, always. So Abel wanted to solve the equation of this is known. So phi n alpha is known, some fixed A as said. And then want to know that to solve this equation. So and then Abel found that Galois group, of course he didn't know that, don't use this notation, but since you know that the name Galois group is abelian, so that you can solve. So algebraically. So actually, Abel is really interested in the case when that equation can be solved by algebraically. So he found some sufficient condition. That condition is today's notation means that the Galois group is abelian. So he gave some condition about the transposition, permutation of the root, and if the permutation root is abelian, only the abelian permutation are allowed, then that equation can be solvable. That he proved before. So he found that he could apply his theory in this situation, so that this can be solvable. So it's a rather surprising relationship with the theory of equation because it's completely different subject. But Abel is really interested in such a solving equation. But if you look at the meaning of this,
But Abel did not know the truth if the equation is abelian, but the Galois group is abelian.
or not.
So
No, he gave a
just Galois knows that.
yeah, but he knows that sometimes that under some condition that is solvable, and that means that actually today's terminology is Galois group is abelian. So he gave some condition on the permutation of the root, and that is precisely the definition of the abelian group of this function. And this is well defined if inside is positive real numbers. But if it inside it becomes negative, then which square root you can choose? It's not so clear. So in that sense, his definition is because he extends phi alpha to the complex domain, and that means that also the value of the phi alpha is already the complex number. So even inside of this root, it's a complex number. And then it's more complicated because it's taking a root. There's a 2 plus minus of some, and which one you choose is not so clear. This. But of course, he chose very carefully. And if you know that today's terminology, you can choose a certain branch of this function. Then you can define that this function well. But in other time, he has no idea about that, so it must be very careful. And also, even for this integral, for example, if t is complex numbers and maybe next week I will talk about the integration along some complex, line inside of the complex. Then 1 minus t to 4 square root, inside is already the complex number. Then you must be careful which root you are taking. There is no, of course, there's a natural way to take that. But in a sense, this is actually not single valued, but this is actually the double valued functions. Then that's what does it mean? You take this integration, and that's also it's really puzzling things. So 1 minus t to 4 is a very simple function, so it's okay. But if you, and also for the other case, it's very concrete function, so you can carefully choose the square root. But if you generalize, for example, average result, actually later Jacobi really tried to generalize average result for the higher degree polynomial square root of px. Then that you must be very careful about how to choose this root. And this is a really difficult problem. But suddenly, this problem was solved by Riemann. And he is really extending the notion of the complex plane to the so-called the ramified covering of the complex plane. So that the true thing is, even though it looks like you are taking the integration along some complex plane or some lines, it's really not true. What you are doing is you are integrating the covering space of the complex plane, which gives you the precise, good definition of this integral. But for that, I really need some preparation, or you need also the preparation to understand. So maybe it's better to stop at this moment here, so that just please remark that this is, in general, if you consider this a complex function, not single value, but double valued, so that the integral is a little bit complicated. So how to remedy this defect in a very nice way? That's the next week's talk. But before going to the average result, probably it's better to talk a little bit about the Jacobi result, because Jacobi has also another very interesting idea that to write down the phi alpha, he used a different notation, phi alpha, not using it's an inverse function, but also you can define that phi alpha as a quotient of the two functions, and which is called the theta functions. And then this gives also the new development in the several directions. Okay. So probably it's better to stop.
Right.
Okay.
And not today. We
Yeah.
stop today.
Today. Yes.